Welcome back to the course. As we progress through Model 2, this session will explore the mathematical relevance of calculus within the context of machine learning models. In this comprehensive session, we'll discover the essential calculus concepts that form the backbone of machine learning models in this in-depth presentation. We break down key topics like derivatives, integrals, partial derivatives, and gradients, highlighting how they power machine learning algorithms and model optimization. Perfect for students and professionals alike, this guide will enhance your understanding of the mathematical foundations behind model training and prediction. Strengthen your skills to build, analyze, and improve machine learning systems with confidence. Understanding derivatives. Definition. The derivative quantifies the instantaneous rate of change of a function, symbolized as the derivative of y with respect to x. Geometrically, it represents the slope of the tangent line at any point on a curve, providing insight into local behavior. Key rule. The power rule states d by dx of x to the n equals n times x to the n minus 1, which simplifies differentiation of polynomial functions, critical in machine learning loss functions. Example. For f of x is equal to x to the power of 3, the derivative of f with respect to x equals 3x squared indicates how quickly the function grows at any x. Integral calculus, the area under the curve. Fundamental concepts. Integrals sum quantities across an interval, representing accumulated change. The fundamental theorem of calculus links derivatives and integrals, allowing calculation of areas under curves by antidifferentiation. Application and example. Integrals calculate exact areas between curves and axes, essential in probabilistic models and continuous data analysis. For instance, the integral of x squared with respect to x equals 1/3 x cubed plus c, where c is the constant of integration, showcases integral calculation with polynomial functions. Partial derivatives, multivariable calculus. Definition and notation. Partial derivatives measure the rate of change of a multivariable function with respect to one variable while holding the others constant, denoted as the partial derivative of f with respect to x. Example. For f equals x squared plus xy plus y squared, the partial derivative of f with respect to x is equal to 2x plus y reveals how f changes with x alone, enabling detailed analysis of multi-input functions. Importance. They allow optimization and sensitivity analysis when multiple features impact machine learning models. Gradients in machine learning. Gradients play a pivotal role in machine learning, especially in optimizing models through techniques like gradient descent. They represent the direction and rate of fastest increase of a function, often the loss function in a model. By leveraging gradients, algorithms iteratively adjust parameters to minimize error and improve performance. The mathematical foundation of gradients. Gradient definition. A gradient is a vector of partial derivatives of a function with respect to its inputs, indicating how much the output changes for an infinitesimal change in each input variable. Gradient in multivariate functions. For models with multiple parameters, the gradient generalizes to multidimensional space, guiding parameter adjustments in all dimensions simultaneously. Role in optimization. Optimizers use gradients to perform steps downhill on the loss landscape, iteratively refining model weights for better predictions. In machine learning, suppose we have a loss function L theta, where theta stands for the model's parameters, such as the weights in a neural network. The gradient of this loss function L, with respect to the parameters theta, indicates the direction in which the loss increases most rapidly. To minimize the loss, we move in the opposite direction of the gradient. Gradient descent, optimizing models. Goal. Gradient descent iteratively minimizes a cost function to optimize model parameters, such as neural network weights, resulting in improved predictions. Update rule. The parameter update follows, theta equals theta minus alpha times the gradient of j with respect to theta, where alpha is the learning rate controlling step size, balancing speed and stability. Use case. This optimization is fundamental to training complex models in machine learning, enabling automatic parameter tuning from data. Gradient descent algorithms. Batch gradient descent. Computes the gradient using the entire dataset, providing precise but computationally heavy updates. Stochastic gradient descent. Approximate gradient using one data point at a time, allowing faster but noisier updates that can escape local minima. Mini-batch gradient descent balances accuracy and computation by using small batches, widely adopted in deep learning for efficient training. Applications across algorithms. Neural networks use gradients to backpropagate errors and update weights layer by layer. Linear regression apply gradients to minimize the difference between predicted and actual values. Logistic regression optimize classification boundaries by adjusting parameters with gradient information. Note: we'll explore neural networks, linear regression, and logistic regression in detail in upcoming sessions. Stay tuned for those updates. Backpropagation, training neural networks. Concept: backpropagation applies the chain rule to compute gradients layer by layer, moving backward through the network to update weights. Process: the error signal propagates backward, adjusting weights to reduce prediction errors progressively with each training iteration. Outcome: this method effectively minimizes loss functions, enabling neural networks to learn complex feature relationships and patterns. Real-world applications, linear regression. Use in parameter estimation. Calculus enables finding parameters that minimize prediction error by setting derivatives of the cost function to zero or using gradient descent for iterative refinement. Example: in predicting house prices from size, linear regression uses derivatives to find the line best fitting the data, balancing bias and variance. Real-world applications, image recognition. Goal: train convolutional neural networks to classify images with high accuracy by optimizing internal filters. Calculus role: backpropagation computes derivatives to update convolutional filter weights, improving feature extraction and classification. Impact: this underpins advanced computer vision applications including medical imaging, autonomous vehicles, and security systems. Conclusion: calculus as a foundation. Essential tool. Calculus is fundamental for understanding and optimizing machine learning models by providing tools to navigate complex functions. Continuous learning. Mastering calculus opens doors to advanced algorithms, innovation, and deeper insights into algorithmic behavior. Future outlook. The ongoing success of machine learning hinges on strong mathematical foundations, reinforcing calculus as an indispensable skill. Acknowledgement and upcoming directions. We appreciate your engagement. In the forthcoming session, we will proceed with Module 2, focusing on the foundational role of probability and statistics in the development of machine learning algorithms. Key topics include probability distributions, Bayes' theorem, statistical significance, and hypothesis testing, emphasizing their applications in improving model performance and reliability. We invite you to subscribe, like, share, and actively engage with our learning resources to stay updated with the upcoming academic content.